The standard normal distribution is often useful to standardize normally distributed random variables. And to do this, we can use the coding data so that it can be modeled by the standard normal distribution. And for a standard normal distribution, it has a mean value of 0 for the standard normal distribution and a standard deviation of 1. And the normal random variable x, which has a mean of mu and a standard deviation of sigma, we can then code it, and we can use the code that x using the formula as follows, where z is the standardized value z, which is equal to the random variable x minus mu, the mean, over the standard deviation. So the standard normal distribution, since it has a mean of 0 and a standard deviation of 1, we can always say that all standard normal distribution would be written as follows. Z can be approximated by normal distribution, or the standard normal distribution, 0 mean and 1 is the standard deviation. Often in a question we'll be expected to find the mean or the standard deviation, or in some cases both. In this example, we look at how we find both the mean and standard deviation from the given information. So we are told that a random variable x is approximated by a normal distribution. And we are given some information here. We're given that the probability of x being less than 17 is 0.8159. So I'm going to first of all go and draw a normal curve. And for this normal curve, I'm going to write down first of all my mean for x, which I don't know. I'll leave it as mu. Then I'm going to write down here z, which is my standardized values, and the mean for z we know is 0. And that's because we can use the standardized normal distribution, where z is approximated by the normal distribution with mean of 0 and a standard deviation of 1. And we're told in this question that x less than 17 is 0.8159. Now 0.8159 is greater than a half, so 17 is going to be on this side, because everything to the left of this value here is 0.8159. So we'll then go and use our inverse normal function on our calculator. So let's go to our inverse normal, and we know the area to the left of 17 is 0.8159, and we're going to use our inverse normal with our standardized values to work out what this value here is. So I'm going to call this value here A. I want to work out what the standardized value A is, such that the probability to the left of it is 0.8159. So let's go and write this down on our calculator. We would go to the inverse normal. And once we've selected the inverse normal here, we then need to put down what our area is going to be. So the area to the left of this value A is 0.8159. We then need to put our sigma for the standardized, since we are using the standardized z values here. So notice here, this is all inverse normal with the standardized values here. So what is our standardized z value? Well, we've already written that down here. Its standard deviation is 1. And what is the mean? Well, its mean is 0. So this is all with the standardized normal distribution. Inputting these values into the calculator then gets us a value for A, which is equal to 0.8976 to 4 decimal places. We're going to now go and use the second piece of information given to us in the question, where the probability of x less than 25 is equal to 0.9970. So again, we start by drawing a normal curve. And the central mean value here is mu, which we don't know for the random variable x. But what we do know is the x value here is 25, and everything, the probability of x being less than or equal to less than 25 is 0.9970. So all of this area here represents the probability 0.9970. Now, the standardized value z for here, the mean is 0, and at 25, at x equals 25, the standardized value z is what we're trying to work out. So we don't know what this piece of information is. So let's go and write down again our standardized z has normal distribution n, 0, and a standard deviation of 1. And again, we're going to use the inverse normal here to work out what the value of b is. So we're focusing on z values here. We're using the standardized z, inverse normal with the standardized values here. And the input in our calculator is going to be, for area, we're going to write down 0.9970 from there. And then for the standard deviation, we're going to use 1. And for mu, we're going to use 0. And then inputting these values into our calculator gives us the value of b to be 2.7478. Now we can go and use these a and b values to work out the mean and standard deviation. We're going to go and use our coding here where x, we're going to go and use our coding here where z is equal to x minus mean over standard deviation. And for this first piece of data, we can say the z value that we worked out here. So the z value is, remember, it's this value that we worked out, the a value, that is 0.8998 is equal to the x value here, which we know is 17, minus the mean, which we don't know, over the standard deviation. So we have an equation here with two unknowns. We can't solve it at this stage. Let's go and take a look at the second set of information that we're given here. And again, start by writing our formula here. Z is equal to x minus mean over sigma. The z value here that we're given is b, which we worked out to be 2.7478, is equal to the x value here, which is 25, minus the mean, which we don't know, over the standard deviation. The mean and standard deviation that we have here is the mean and standard deviation of the random variable x, not the standardized normal. And this is what we're trying to work out. We're trying to work out these values, the mu and the standard deviation. Now, since we have two equations here, equation number 2, equation number 1 here, with the two unknowns, sigma and mu, we can then go and do simultaneous equations to work out these two unknowns. So let's go and take a look at how we complete this question then. So rearranging this equation, we get 0.8998 sigma minus 17 is equal to minus mu, and this equation gets us 2.7478 sigma minus 25 is equal to minus mu. We can subtract one equation from the other, and that will then eliminate our mu value here. So subtract one equation from the other. Right, the other equation here is 0.8998 sigma minus 17 equals minus mu, and we are going to subtract one from the other. So we get 2.7478 minus 0.8998, which gives us 1.848 sigma. And then we have minus 25 take away minus 17, which becomes minus 25 plus 17, which is minus 8, is equal to, get 0 there. And so then we can go and find out what sigma is. Sigma is equal to 8 over 1.848. And that gives us sigma is equal to 4.33 to 2 decimal places. We can then go and substitute this into one of our equations here to find out what mu is. Let's go and use this equation here. 0.8998 lots of 4.33 minus 17 is equal to minus mu. So we have minus 13.10 is equal to minus mu. Therefore, we can say mu is equal to 13.10. So we've worked out the mean and standard deviation of the random variable x.